We're talking about RL circuits this week and measuring the RL time constant. And it's very similar to what we did for the RC circuits way back when, whatever it was, in lab 3 or 4, measuring the RC time constant. But this time we're going to do it a little differently. Last time we chose a value for R and a value for C that were very high, and it gave us a very long time constant, and we were able to observe it just by watching a voltmeter with the video camera, and you got your data that way. This time we're going to do it a little differently. We're going to do it the way you would have done it in lab. I'm going to do it the way you would have done it in lab, and I'll record the data onto the oscilloscope. So we'll use an oscilloscope because the signal is changing so rapidly you really can't detect anything by watching it. And I will record it with an oscilloscope. And these modern oscilloscopes, digital oscilloscopes, you can download the data file. You've already done that once. You'll do that again this week. You'll open the comma-separated value, the CSV file, into a spreadsheet program like Excel or Google Sheets, and you can plot the data. So we'll be measuring the RL time constant. We have a resistor and an inductor in series. This is an RL circuit. What happens when we throw that switch to position 1, as we on the left, the diagram on the left, when we throw that switch to position 1, the battery starts to push current, but we have a loop of wire there, right? That inductor is just a coil of wire. It's like a solenoid. Current starts to flow through it, and when the current flows through it, a magnetic field is generated by that current, magnetic flux through the coil, and that creates a back EMF, we call it. It creates a current in the opposite direction. It pushes back hard. So the battery tries to flow current in one direction, and the coil of wire tries to flow current in the opposite direction due to that current. And there's a standoff for a fraction of a second. No current flows. And then the current from the battery keeps trying and starts to work its way through, and eventually it ends up being at its normal value, and that inductor has no effect on the flow of charges in the circuit. Because only when it's changing, only when there are changes, does it affect the circuit. So throwing the switch to position 1, the battery tries to push a current through, and the inductor pushes back, and at that instant no current flows, but eventually the current makes it up to its steady value. So let's take a look at what that graph looks like. It looks like this one. I call that increasing current. Increasing current. When we move the switch to position 1, the instant the switch is closed, the inductor pushes back hard. We're looking at current in the circuit here as a function of time. The inductor pushes back hard and no current flows, but after time things stop changing as rapidly, and so the inductor doesn't push back as hard, and as t gets longer and longer, as time goes to infinity, the current approaches its maximum value. What is the maximum value? It's just the voltage divided by the resistance in the circuit. It's as if the inductor is not there. It's just a coil, it's just a piece of wire at that point. We could also look at the voltage across the inductor, but for our purposes of this lab, we'll be looking at the current during the decreasing. We'll only be looking at this equation down here for decreasing current. Let's talk about that now. Now we're going to take the switch from position 1. It's been in position 1 for a long time, and move it to position 2. We're going to remove the battery from the circuit. When we do that, there was current flowing through the solenoid. There was current, and it was creating some magnetic flux through the solenoid. And then we all of a sudden removed that current. But the solenoid had magnetic flux through it. It doesn't like changes. It doesn't want to go to zero. So it acts like an EMF source and tries to keep the current going, keep pushing it in that direction to keep the magnetic flux the way it was. It doesn't like changes. It doesn't always oppose the flux. It always opposes the change in flux. So when we hook up the battery, when we throw it to position 1, the current starts up, creates flux that wasn't there before. So the solenoid creates, the inductor creates current in the opposite direction to try to get the flux back to zero. But when we're at position 1 for a long time, there's a lot of magnetic flux through the solenoid, through the inductor. And when we throw that switch to position 2, it doesn't want to go to zero. It wants to keep it where it was. So it pushes the current, keeps pushing the current, creates an EMF in that direction to keep current flowing, to keep the flux at the higher level, at least for an instant or two. That looks like this if we were to graph it. You take that switch, you had nice constant current flowing, and at t equals 0 here, you remove the battery. The current doesn't just drop to 0 instantly. It slowly decays to 0 over time as the inductor stops acting like a battery in that direction. So this, I call this decreasing current because we've removed the battery. I call this increasing current because we had none and we added a battery which tried to flow current through the circuit. And here we had a battery flowing current and we removed it from the circuit. So I call this one decreasing current. You have to, it's like the capacitor. Remember, we had a set of equations for charging the capacitor, and we had a set of equations for a discharging capacitor, and they were different. It's the same thing with the inductor. We have a set when we're trying to increase the current by hooking up a battery, and we have a set of equations when the current is dropping when we remove the battery. And make sure you get the right initial conditions. Put t equals 0 in and t equals infinity in, and make sure you're using the right equations. How are we going to do this switch thing? With the RC lab, the R and the C were so big, it took, 56 seconds or something to hit the time constant? We could just push a button, change the switch, and you could watch over a minute, 2 minutes, 5 minutes. You could watch the changes. Well, this time we can't do that. What we're going to use is a function generator set to a square wave instead of a switch and a battery. And that function generator set to a square wave, it's going to put out a voltage and then it's going to drop to 0, put out a voltage, drop to 0, and that's what the square wave is. It's actually not quite that simple. We'll talk about that later. But that's basically the square wave. It's like turning a switch on, off, flipping that switch from position 2 to position 1, to position 2 to position 1, back and forth 1,000 times a second. And we can capture that on our oscilloscope, and it'll look something like it does in this image here. That's what we expect, right? As time goes on, the current goes up to its maximum value, then it decays back towards 0 and back up to its maximum value. You can see the pattern there. And it's the same type. You do your loop equations and solve a differential equation, and you end up with these exponentials. That's where these come from. Let's take a look. So what you're going to do is the same kind of 3 methods. Method 1, we're just going to get the time constant from L and R. But this time it's a little different. Remember, with R and C, the capacitance, we multiplied them together. R times C was the time constant. But here, tau is equal to L divided by R. L divided by R. So we can get those values directly and just divide L by R. Then we have a single point measurement. You'll have all this data, and I'll walk through one for you here. I'll walk through how to do this. We'll have all the data, and then we'll look for that one point when the signal drops to 1 over e of its maximum value, and the time it takes to do that is our time constant. And then we'll do the multiple point method. And this one, you can use the data file that's going to be available to you. And there's a lot of points. There's over, what is it? There's 2,500 data points. But you'll see when you plot it that it gets very noisy at the end. It really, the tail gets very, very noisy. And you're going to have to cut some of that data out. I think you'll probably end up using, somewhere between 500 and 700 or 800 data points, somewhere in there. And that'll work very nicely. You don't want to use all 2,500 because as when things aren't changing, any little variation becomes a lot of noise. The data really becomes error-filled. And you're going to use the exact same techniques. When you do this method 3, we're going to linearize it by taking the natural log of both sides and plotting the natural log of the voltage versus time. And when we do that, then the slope is negative 1 over your time constant. So that's how we're going to get the slope, the tau, the time constant. And how are we going to get the error in that? From Linus. It's the exact same techniques you used for the RC time constant lab. Okay, let me show you method 2. There's a little tricky part here we have to walk through. Because what the function generator is actually doing, it's not outputting 0 to V maximum, like we're expecting here, right? We're kind of expecting it to be 0 to V max. But it's not. What is it doing? It's going negative V max over 2 to positive V max over 2. It has this range. So what we have to do is find the minimum point here. I'm calling the maximum point on our graph V1 and the minimum point V2. We have to find V2, which will be, I don't know, negative 4 volts, negative 5 volts, something like that. And we have to add the absolute value of that to everything because we want to make this minimum 0. We want to take this whole scale and shift it up by V2. So we make V2, instead of negative 4 volts, we make it 0. Shift the whole thing up so that 0 is our lowest point. Once we do that, then we can do everything normally. Okay, so let's bring up some sample data. Data is a little different than yours. I used a different inductor, but other than that, so the numbers I'm getting will not be the same as what you're getting. You're going to open up a data file, and it's going to look something like this. You're going to have multiple columns. One column is just going to be the square wave that the function generator generates when it's not hooked up to anything. One file that shows multiple cycles on the oscilloscope. And then we're going to zoom in, we're going to enlarge the view by changing the scale, and then one of your data sets will be that enlarged view. That's the one you want to use. So this says right here at the top, enlarged view of one cycle. And if we plot this, I'm just going to select the whole thing and do a scatter plot. And that looks similar, right, to what you saw on the oscilloscope when we zoomed in. When we had multiple cycles, when we weren't zoomed in, you saw multiple cycles like this, right? But if I zoom in, now we're only looking at kind of one cycle with a little tail on each end. Here's our maximum, and it drops to 0 as time goes on, and then the next cycle, then it charges, right? At the next cycle, current starts flowing, and it repeats. Well, the first thing you have to do is trim the two tails off. We don't want those parts of the other cycles there. We only want the one decaying function here. So we have to find basically this point here, and that occurs at about negative 0.002022. 4. So I'm at the beginning, and I'm looking for the point where they starts to drop very rapidly, and I haven't seen it yet. 4.24, 4.24, 4.24. Oh, now it's dropping very rapidly, right? So I would say the maximum occurs, the point where things really start to change occurs about here. I would say one of these is my 0 point, t equals 0. Okay, so I would call this t equals 0, and then things really start to drop after that. You see that? Pretty constant, 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 a little variation, and then all of a sudden from here it goes down, 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 and it drops pretty quickly. So this is what I'm going to call t equals 0. So I could just get rid of I'm not going to use any of this. I could just delete this, and it'll shift the cells up. That's fine. I can do that. This is not t equals 0 anymore. Okay, so now, where's my graph? My graph is way down here at the bottom. Now you can see what happened to my graph. I just got rid of all of this stuff before it started to drop. Now I can do the same thing at the end here. I want to sort of get rid of the stuff at the end. So that's in here. So it's negative 4.24 volts, negative 4.24 volts, nice and constant. You know that out there at the end it was hardly changing at all, and then it abruptly started to rise again. So we're looking for that point. We want to get rid of the points when it starts to rise again. Oh, right here. So you can see this is all the same, and all of a sudden it starts to rise. So I would cut it off about here. We can just get rid of all this stuff. This is as it's right. This is part of the next cycle. We don't care about this stuff. I can just delete that, and it doesn't matter. There's nothing there. Okay. So now I've trimmed it, and where's that graph I had? It's floating down here somewhere at the bottom. And you can see this is what I wanted, right? I wanted it to look like the graph in my handout, where it starts at its maximum value and it decays out to 0 as time goes on. So that's perfect. Now, so that was the first step. Second step is to offset. I don't want any negative numbers. I need it to be from 0 to some maximum value, because I'm going to take a natural log of this, right? I'm going to linearize the data by taking a natural log. So I'm just going to get rid of this chart because it's not where I want it anyway. I'm going to create another column here. I'm going to call this, what am I going to call this? V plus V min. How about that? I'm going to add the minimum, the absolute value of the minimum, to all my voltages to shift the whole thing up. So what's my minimum voltage down here at the bottom? Whoa, went too far. 4.24, negative 4.24. So I'm going to add 4.24 so that everything becomes positive. So now I'm going to add 4.24 volts to everything so that this becomes 0 at the bottom instead of negative. So I go back up here and I say, I put in an equal sign, right? That's how you tell Excel there's an equation there, equal sign. And then we'll do this cell. I'm going to click on the cell with voltage, and I'm going to add 4.24 volts to it. And then I'm going to just drag this down. Did you see how I did that? When you move the cursor to the lower right corner in Excel, I think it does the same thing in Google Sheets. It changes, and you can click and drag, and it fills down. So this is going to be B5 plus 4.24, and this is B6, which is this one, plus 4.24, right? It's just adding them up. And I can go all the way down to the bottom, or you can use the fill down command if you like. A little bit more. There was about 2,500 data points there before I trimmed the ends. All right, now I've offset my data so that it goes from 0 to Vmax instead of negative Vmax over 2 to positive Vmax over 2. 0 to Vmax. So that's good. Now I can do part B here. Or I should say method 2. Method 2. Let's bring up the handout. Method 2, we're going to just do a single point measurement. So we need to we're looking for the time it takes to get to 1 over E of its maximum value. Yes, question was, can we just use the minimum function in Excel to find the minimum? Yes, you could do that. That's a good way to do it. Here, let's do it real quick. You could have done here, you could have done equals this plus, actually not plus, minus, because it's negative, the minimum of B2 to B, let's just do a quick scan here, whoa, too far, to B, what is that? 1904. 1904. B4 to B1904. There we go. But we're going to copy this down. We want the first B4, we want that to change to B5, B6, B7 as we copy it down, but we don't want these to change. We want these to stay the same. So we'll put a $sign in front of those, and that will lock them. And now we should get the exact same thing. Do we get the exact same thing? 56, 64, 72, 6.8. It looks exactly the same to me. Yeah, that would work very well. Good. Love it. Okay. So we've got our data all offset, all shifted up where it needs to be. Now, if we look back at our, let me go back to this. Now, if we look back here, we're looking for 1 over E. We're going to take our maximum value and multiply it by 1 over E of the starting current. And then we're going to take how much time it takes to decay from its highest point to 1 over E of its highest point. So let's go back to, and I'm just going to use my calculator. It's telling me e to the first power is 2.71828. I can take 1 over that. I get 0.36787. And I multiply that by 8.48 in my case here, because my data is a little different than yours will be. I got 3.12. So I'm looking for the voltage, column C, to be 3.12 volts. Now you can see that it's changing so fast that there are a number of points that fall into this category. I'm just gonna, what am I gonna do? Pick the middle one? Doesn't matter. So I'll take this value, negative 0.00187 seconds. Okay, that's my T2. My T1 is this time right here. This is my 0, right? And my delta T is tau. So this is one of these minus the other one. I don't care which order I do them. I'll do them in the other order, I guess. So it's a positive number. Okay, so this is my delta T. From T equals 0 to the time it dropped to 1 over e of its maximum value is this much. So there's my time. That's tau. That is tau. 153 microseconds. Okay, that's method 2. And then for method 3, we have to take the natural log of this, right? Let me go back to the handout. And the handout kind of walks you through it. I'm not going to divide by V0. I'll just get a y-intercept. If I don't divide by V0, I'll get a y-intercept here. That's the natural log of V0. That's okay with me. All I care about is the slope of this thing. So I'm just going to plot the natural log of VR. You could divide by V0 if you want to. That's fine. I'm just going to divide the natural log of V, the voltage across my resistor, right? That's telling me that's the same as the current in the circuit. It's proportional to the current in the circuit. So the natural log of the voltage against time and negative 1 over tau is what the slope should be. So let's go back and look at our data. We're almost there, right? We've got the data offset, but we don't have the natural log of that. So we're going to do natural log of V plus V min equals ln of this guy. And then we can fill this down. And then we want to plot this versus time. Time on the horizontal axis. Scatter plot. So we want to get rid of these two. We only want our linearized data. There's the linear data. And we see how what happens with this is, well, first of all, we've got a natural log of 0. I think that's given us some problems. So I'll get rid of that. And then you can see that as we get out to the bottom here, because it's not changing very much all the way out the bottom, any little noise, any little fluctuation becomes a lot of noise. So I would trim this way down. I would cut out almost all this stuff where that tail starts to fan out. So I'll show you what I mean. Let's just start moving these up. You can see we can start to get rid of some of the data here. But I want to go to like maybe 0.0015, kind of right around there, negative 0.0015. So I'm going to just get rid of this, and we'll do it again. We'll start at the top and go to 0015. And I'll do a plot, scatter plot. And I don't want those two in between. I just want the column, the linear one. There we go. Well, that's not very linear. So that's the data that you have is a little better than this. It's very nice and linear. But you have to get rid of all those points at the end where it really starts to fan out and focus on the first, I don't know, 500, 600, 700 data points, something like that. And you get a really nice line. So we'll do a linear trend line with the display the equation. Oh, you know what else we need to see is the trend line. There it is. So now we can see the trend line. So this data is not actually that great, but the data you have is much better. It really fits that trend line nicely. And so what does this give me? This gives me 4109. Gives me 243 microseconds. Okay, so my two numbers differ quite a bit. I went from 153 microseconds using method 2 to 243 using method 3, but the data doesn't look that great. Your data looks much better, very linear, and your time constant should be reasonably close, within 10% of each other for sure, maybe less than that. All right, so I walked you through the methods, right? And you have to remember to go back and do the linist in Excel to get the uncertainty in the slope here. The only other tricky part here is method 1, actually. Method 1, let's go back and look at our handout. Method 1 is just L divided by R. Now the L is printed on the board we're using, so we can just use the value that they give us. And I would probably go with plus or minus 5% on that. R is printed on the board, and we can go with plus or minus 5%. But here's the thing you have to remember. When it says here, remember, ideal power supplies have no internal resistance, and ideal wires have no resistance. But we are doing this experiment in the real world. And what that means is that coil of wire, that inductor, it's a coil of wire. Normally we just think of wires as having almost no resistance. But this is a ton of wire, a lot of wire wrapped around and around and around and around and around to make a nice coil. And there's so much wire there, there's actually, we can measure the resistance of that. It's somewhere in the 5 to 6 ohm range. So 5 or 6 ohms, it's not a lot, but the resistance that we're using is only 100 ohms. So if we ignore it, we're introducing 5 or 6% error in our results right off the bat. The other thing we have to remember is that function generators, power supplies, batteries have internal resistance. And we have to take that into account also, because our resistance is so small in this circuit, 100 ohms, that would have a big effect. So we need to look at all those things when we calculate the total resistance in the circuit. Why didn't we need that for our RC circuit we did a few weeks ago? We didn't care about the internal resistance of the battery. We didn't care about the wires, because we had a huge resistance there. We had a 48,000 ohm resistor, something like that. So if your battery has 5 or 10 or even 50 ohm internal resistance, and your wires have 2 or 3 ohms resistance, who cares? Out of 48,000 ohms, that's not introducing any real error, right? That's not even changing you by 0.1%. But here, we only have a 100 ohm resistor in our circuit. So any little bit, a couple ohms here, a couple ohms there, all of a sudden you're talking 5, 10%, 50%, you're off by. So you have to include those.